Good morning. Today we're going to be talking about section 4.2 entitled Solving Compound Inequalities. Well, what does compound mean? Well, it really means inequalities made up of other inequalities. For example, if we are asked to solve this inequality statement, minus 3 less than or equal to 2x plus 5, which is in turn less than 7. Alright, this is what we call a compound inequality. In particular, this is a double-sided inequality for obvious reasons. And double-sided inequalities are really what we call AND statements. Double-sided inequality. Oops, hang on. Double-sided inequality. Really what we are doing here is solving two inequalities at the same time. We are asked to solve this inequality, 2x plus 5 is less than 7, and this inequality, that minus 3 is less than 2x plus 5. So really double-sided inequalities of this type are really AND statements. You're asked to solve 2x plus 5 is less than 7. Excuse me. And minus 3 is less than or equal to 2x plus 5 simultaneously. Alright, let me rewrite this. Alright, in this type of situation where you've got a double-sided inequality, my goal here will be to do algebra type things to isolate your variable in the middle of these two inequality statements. And to that end, we'll do similar things we did in section 4.1. Well, to that end, I'm going to subtract each element of this inequality statement by minus 5, kind of your goal being to clean up the middle part. Minus 8 would be less than or equal to 2x, which is in turn less than 2. Alright, now of course I'll multiply each piece, each element of this double-sided inequality statement by positive 2. Again, your goal being to isolate variable in the middle. Alright, you're dividing by a positive quantity, so I leave the arrow alone. I leave the arrows alone. So I'll get the resulting statement, minus 4 is less than or equal to x, which is in turn less than 1. Alright, this is my solution set. Now let's take a look at this for a minute. And investigate what this really means. Alright, this statement tells me I want all real numbers such that x is less than 1, and at the same time I want x greater than minus 4. Now, be sure you can read this green circle clearly. If I read it left to right, it's minus 4 is less than x, but if I read it right to left, it's really x greater than or equal to minus 4. So here you're going to have to get used to reading some of these inequality statements right to left. Let me rewrite that, and I'm going to seek to graph this solution set. I want all real numbers such that x is less than 1 and x greater than minus 4. Let me write that down. We need all x values less than 1 and greater than or equal to minus 4. Let me write that in, greater than or equal to, don't forget about that equality, or equal to minus 4. Alright, I'm going to label this as my solution set. And if I seek to graph these numbers, well, x is less than 1. That means x is to the left of 1 on the number line. No equality here in this inequality statement. So I draw an open circle at the boundary 1. So I want everything less than 1 and simultaneously greater than minus 4. Alright, so I'll draw less than or equal to. Of course, equality is included here. So I'll draw a closed circle at the boundary of minus 4 and simply all numbers in between. So very similar to what we did in section 4.1. Really, you're solving two inequality statements at the same time. So there's my solution set, and there's my graph. Alright, our textbook, again, in the answer section, they might give the answer in this form. You want everything above minus 4, including minus 4. So our book might give the answer in interval notation with a square bracket indicating a closed set on the left, meaning the boundary value of minus 4 is included, and everything to the left of positive 1, and we do not include 1 on the right side. So this is what they call a half open or half closed interval. And we're ready for the next problem. Okay? Let me get a fresh screen here. Alright. Let's try another one. Solve. Again, another compound inequality. Minus 6 is less than minus 3 times x minus 4, which is in turn less than or equal to 24. Alright, again, this is an AND inequality statement. It's a double-sided inequality statement. And our goal would be to isolate the variable in between, in the middle, so to speak. And to do that, I'm going to have to, of course, perform this multiplication to free up our x variable from the parentheses, performing my distributive law on that inner segment. I get this resulting statement: minus 6 is less than minus 3x plus 12, which is in turn less than or equal to 24. Of course, I'm going to subtract 12 from each element of this inequality statement, and I leave the arrow alone because I'm adding or subtracting a quantity from all three sides here. We leave the arrow alone. Alright, I'll get minus 18 on the left. In between, the 12 and minus 12 cancel out. Minus 3x in between. And on the right, 24 minus 12 is, of course, 12. So 18 is less than minus 3x, in turn less than or equal to 12. Alright, of course I'm going to multiply each piece here through by negative 3, or divide by negative 3. And that will isolate an x in between, and of course I'm pausing to draw the inequality statements because when I divide or multiply by a negative, you must reverse the inequality arrow, or arrows in this double-sided case. Okay? On the left, minus 18 over minus 3 is, of course, positive 6. Is greater than, well, in between, in the middle, the minus 3's cancel out, and I'm left with x, which is what I wanted, which is in turn greater than 12 over minus 3 is, of course, minus 4. Alright, so here is my solution set in a double-sided inequality statement. Let me label it. Now, let's graph it. Again, this is really an AND statement. This is saying, really, I want all x values that are greater than minus 4, greater than or equal to minus 4, and simultaneously I want all x values that are less than 6. Again, be sure to convince yourself this statement in green says x is less than 6. If 6 is greater than x, then x is less than 6. So I can go ahead and graph. this solution set on the number line? Well, greater than -4, greater than or equal to -4, indicates all numbers to the right of -4, including -4. Simultaneously, I want all x values that are less than 6. So everything to the right of -4 and to the left of +6. Notice at the -4, I have equality, so I draw a closed circle in at -4. And at 6, it's an open set, so I draw an open circle and shade in all numbers in between. Alright, so there is my graph of the solution set. And notice, again, let me briefly state, the author might put a parentheses at the upper boundary indicating an open set on the right, and would, again, the author would probably indicate this with a square bracket indicating a closed set at the left boundary. But I think most of us would be happy with just the open circle or the closed circle, of course, properly placed. Okay. Alright. Also notice the book might give an interval notation for the solution set, and in interval notation the answer would look like this, except you've got to have a closed bracket, a square bracket at the left boundary. Everything between -4 and 6. Okay? Alright, let's try another one. I believe this one's from your textbook. This is number 68. I'm sorry, number 70 on page 345. And let me make sure I copy it down correctly. -2 is less than or equal to 5 minus 3x over 2, which is in turn less than or equal to +2. Again, a double-sided inequality, or an AND type inequality statement. Again, the goal is going to be to isolate x in the middle, and I see if I multiply all three elements by +2, I'll get rid of this fraction in between. So let me go ahead and indicate this. Multiplying each element by +2. On the left, I'll get a -4 is less than or equal to, well, of course, the 2's cross-cancel here, less than or equal to 5 minus 3x over 1, which is, of course, 5 minus 3x, which is in turn less than or equal to +4. Alright, I can solve this one fairly easily now. Again, your goal is to isolate the variable in between. I'll subtract 5 from each piece, leave the arrow alone. I'll get -9 is less than or equal to minus 3x, is in turn less than or equal to -1. Alright, and here now I will divide each element by -3. And again, I'm going to pause because you know what happens. When you multiply or divide an inequality through by a negative quantity, you reverse the inequality arrow. So I'm going to pause for a minute, indicate that very clearly. So I get a greater than here and a greater than or equal to here, right? Alright, let me clean this up now. -9 over -3 is, of course, +3. Is greater than or equal to, well, of course, in the middle, -3's cancel out. That's what we wanted. Give me an x all alone in between, which is in turn greater than +1/3. So 3 is greater than or equal to x, which is in turn greater than or equal to 1/3. This is my double-sided solution set, and now I've got to graph the solution set. Well, if I graph this, again, we've got to read this really one equality at a time. this statement tells me x is greater than 1/3. Actually greater than or equal to 1/3. So let me indicate that. I'll put 0 here, and 1/3, positive 1/3, is somewhere to the right of 0. I'm going to want to close circle here because equality is included in this boundary value. And I want to shade in everything to the right. Let me pause for a minute because I've got another inequality statement to worry about. This statement in green tells me 3 is greater than or equal to x, which means x is less than or equal to 3. Less than or equal to 3. Well, so I'll draw a closed circle in at the boundary value of positive 3. So if I'm satisfying both of those inequality statements simultaneously, I get all real numbers on the number line between 1/3 and 3. So there's my solution set, and there's my graph. Alright, so we've done 3 n-type inequalities. I want to talk about or-type inequalities next. Those are also compound inequalities. And basically there are 2 inequalities linked with an or statement. Well, let's start out nice and easy. If I want to graph this or statement, this tells me x is less than or equal to -2 or greater than positive 6. And or in the mathematical sense, it really means union. Basically, I'm satisfying one of these inequalities or the other inequality to be in the solution set. So x less than or equal to -2, let me put 0 here. It's a reference point. Less than or equal to -2 means left of -2, of course including -2. So this stretches out to negative infinity, and I'll indicate that with a nice bold arrow, shading everything to the left of -2. Or greater than positive 6. I'll put 6 up here somewhere. Alright. Strictly greater than, well, it means an open circle at the boundary value of 6, and greater than 6 means to the right of positive 6. Alright, so typically in these or situations, you end up with a broken interval, what I call a broken interval for obvious reasons, on our number line. Okay? Alright, let's look at something more substantial. Solve the following inequality or statement. X over 2 is greater than 2, or -3 times x minus 2 is greater than 0. Alright, so the solution set will really be the union of solutions to both of these inequality statements. The one on the left branch, I can solve pretty easily. I'll just multiply both sides by 2, and I get x is greater than 4. Or, let me work on the right-hand branch here now. If I solve for x in the right side inequality statement, of course I've got to apply my distributive law. Minus 3x plus 6 is greater than 0. If I subtract 6 from both sides, I get minus 3x is greater than minus 6. And again, to clean up x on the left-hand side, I'm going to have to divide by a minus 3. And when you divide or multiply by a negative, you've got to reverse the inequality arrow. So minus 3x over minus 3, of course, reduces to x on the left, is less than 2 on the right. So let me carry this down. I get x as my solution set. X is greater than 4 or x is less than 2. So let me circle that. This is my solution set. And notice, to be correct, you need to actually write down that OR statement in your final answer. X is greater than 4 or x is less than 2. Let's graph this solution set. I'll put 0 here. X is greater than 4. Well, greater than means to the right of, and strictly greater than means open circle at the boundary value of 4. Nice and bold. Or x is less than 2. Well, less than 2 means everything to the left of 2. Strict inequality, open circle. And shaded in real bold, okay? So x is greater than 4 or x less than 2 gives me that resulting graph. In this type of problem, our author would probably indicate open sets with a parentheses on the number line graph. And let me make a note how the author might illustrate this solution set. Let me rewrite it. X is greater than 4 or x is less than 2. The book, just to show you where their answers are coming from, the book would probably indicate this set in this fashion. In interval notation, everything to the left of 2 would be indicated with this interval. Everything to the right of 4 would be indicated with this interval. And again, OR means set union, and the author would probably indicate that with the set union symbol. Alright, I think most of us would be more comfortable with this notation, and that's fine with me. Okay? Alright, one more of these OR types. That means we will have done 3 of each. And I believe this is from your homework list. Solve the following inequality statement. This is number 68 on page 345. A over 2 plus 7/4 is greater than 5, or 3/8 plus a over 3 is less than or equal to 5/12. Now, don't panic. We got a lot of fractions here. Well, we know how to get rid of the fractions, right? OR means just that. You have to solve one of these inequalities or the other to be in the solution set. Let's see, on the left-hand side, in the left branch, I would multiply both sides by the LCM of all these denominators, and of course that's 4, right? 4 is the LCM of 4 and 2. So 2 goes into 4. Let me apply my distributive law. 4 times a over 2. Well, 2 cross cancels into 4 twice, and 2 times a is just 2a. Let me put that in yellow. Plus 4 times 7/4 is, of course, 7. Which is, of course, greater than 5 times 4 is 20. So 2a is greater than 13, subtracting 7 from each piece. And a is, of course, then greater than 13/2. So that solves the left branch of this inequality or statement. And let me now work on the right branch here. Well, again, I'm going to want to multiply everything through here by the LCM of all these denominators. What's the LCM of 8 and 3 and 12. Of course, it's 24. Squeezing this in here. But again, I'm going to have to apply my distributive law, multiplying, at least on the left-hand side, both of those terms by 24 independently. 24 times 3/8. Well, 8 cross-cancels into 24 3 times, and 3 times 3 is 9. Plus 3 goes into 24 8 times, and 8 times a is 8a. On the right, 12 goes into 24 twice, and 2 times 5 is 10. Beautiful, no fractions. Equivalent statement with no fractions. Alright, here I would subtract 9 from both sides, and I'll then get 8a is less than or equal to 1. And now, of course, dividing both sides by positive 8, I'll get a is less than or equal to 1/8. Alright, so here is my solution set. Again, you've got to link these with the word or it's incorrect. Let me rewrite it. Solution set a is greater than 13/2, or a is less than or equal to 1/8. I'll put these in brace notation. Alright, now I've got to look for the number line graph. Alright, let me put 0 as kind of a reference point. Well, a is greater than 13/2. What does that mean? That means everything to the right of 13/2 on the number line. Now 13/2, I'll put it up here somewhere. It's like 7.5, isn't it? So 13/2, I draw an open circle because that's a strict inequality, and shade in everything to the right. Greater than means to the right up. Now we're about the left branch. Simultaneously, we want a less than or equal to 1/8. Well, 1/8 is certainly less than 13/2, so I'll put 1/8 here somewhere. And less than or equal to, again, this is equality, means the boundary value of 1/8 is included. So closed circle at 1/8, and less than means left of, everything to the left of positive 1/8. Alright, so there's my solution set, and there's the graph of my solution set on the number line. Alright, so we've done 3 of each, the end type inequalities, the double-sided inequalities, and also 3 of the or type inequalities. So we'll call it a day. This concludes section 4.2, solving compound inequalities.